Welcome to MSB lecture series on main group chemistry. In my last lecture, while discussing about the chemistry of hydrogen, I did mention that the melting points and boiling points for p block elements follow some trend. However, in some groups those trends are violated. So, let us look into those things. That means, when you look into some of these physical or chemical properties in a particular group, generally the melting and the boiling points of a series of related molecular compounds increases with increase in the molecular size owing to an increased number of intermolecular dispersion forces. This is seen for example, along a homologous series of alkanes, that is in case of group 14 hydrides of carbon. If we consider CH4, methane, ethane, propane, butane and pentane, and if we look into the melting point and boiling point, they are steadily increasing. And here, as more and more CH2 groups are added, more and more groups are available for to have intermolecular dispersion forces will be generated. So, as more and more dispersive force centers are generated, as a result what happens, the association between these molecules increases, and as a result they come close to each other, resulting in melting and boiling point increase. So, that means then what would happen to the melting and boiling points of p block hydrides. So, this trend is for group 14 elements. Hydrides follow the same trend as expected, as I had mentioned earlier, but in case of group 15, 16 and 17, the first member of the group behaves in a different way compared to their higher congeners. That means, for example, in case of group 15, nitrogen hydride or ammonia, or in case of group 16, water, or in group 17, hydrogen fluoride, they behave little different than the rest of the elements. That means, essentially these hydrides, first member from 15, 16 and 17 show remarkably high melting and boiling points compared to the rest of the congeners. So, why that happens? For example, if you take melting point and boiling point of ammonia and water and hydrogen fluoride, they are remarkably high compared to rest of the hydrides in their respective group. Let us look into this, what makes these compounds to show different properties. Let us to analyze these trends, let us look into the melting points of several hydrides of group 14 to group 17. I have listed here, for example, CH4, so methane, silane, germane and stannane is given here, and similarly for group 15, ammonia, phosphine, arsine and stebine is there. And in case of group 16, water, hydrogen sulfide, hydrogen selenide and hydrogen telluride are given. And similarly for group 17, HF, HCl, HBr and HI are given. You can see the trends. Trends from the second element follows the expected order, that means steadily increasing their melting point with increase in the atomic number or atomic weight of the corresponding hydride, or when we proceed down the group with for heavier elements, this melting point is increasing. But you can see anomalies here. Water shows around 100 degree and whereas ammonia shows different, HF shows different. If you extrapolate this one backward, you expect them to have much lower than what it is seen here. So, these trends can be explained using hydrogen bonding concept, and of course, same analogy one can make for boiling points also. You can see here boiling points also, to begin with we have highest boiling point for the first member like water, hydrogen fluoride, ammonia, and whereas in case of group 14 no such trends are observed. So, methane shows where exactly it is supposed to be according to the expected pattern. So, that means it seems group 14 elements follow this trend, whether we take alkane series or silane series or germane series, whereas these trends are not followed, and the hydrides of first element show remarkably high melting and boiling points. Okay. So, for this one I have just chosen two sets of compounds here to verify their boiling point. I have chosen group 14 hydrides such as methane, silane, germane and stannane, and in case of group 16 water, hydrogen sulfide, hydrogen selenide and hydrogen telluride are considered. You can see in absence of any anomaly, water is expected to show a boiling point of -100, but that is not the case. We all know that the boiling point of water is 100 degree centigrade, that means it deviates. Why it is deviating? That can be explained again very effectively using hydrogen bonding concept. If you take a water molecule, we have these polar covalent bonds, and here we all know that because oxygen is being more electronegative, it carries delta minus and both the hydrogen atoms carry delta plus. Okay. When it comes in contact with another water molecule, it orients in this fashion and there establishes a interaction between H plus, and this is hydrogen donor and this is hydrogen acceptor. This is hydrogen donor and this is oxygen is hydrogen acceptor. Because of these interactions, this O and H, two molecules come together. That means a water molecule can show 4 such interactions. Let me show you all 4. One can keep writing like this. So, that means each H2O molecule participates in 4 hydrogen bonding interactions, and this is spread across the entire molecule or association, okay, something like this. As a result of this one, what happens, all these water molecules come very close to each other and they are held firmly, and as a result what happens, enormous energy is required to melt these molecules, to separate these molecules. So, hence they show very high melting and boiling point compared to hydrides of rest of the elements in the corresponding groups. So, one can also represent hydrogen bonding in this fashion. Okay. So, these interactions individually, if you take these interactions are very weak, collectively these interactions are enormous in case of water molecule due to the infinite number of hydrogen bonding interactions that we come across. So, this brings these molecules close to each other and increasing their density and increasing their boiling point and melting point. And okay, you can see how these molecules are arranged in the lattice. So, that means hydrogen bond enthalpy is in the range of +4 to +40 kilojoules per mole. They are weak. They are weak compared to HCl bond enthalpy of 431 kilojoules per mole. Hydrogen bonds are stronger compared to van der Waals forces that exist between the molecules. Hydrogen bonding interactions are much stronger than van der Waals forces that exist between the molecules, such as methane molecules or ethane molecules, etc. Okay. And ice has extensive hydrogen bonding. and hydrogen bonding is responsible for the double helix structure of DNA, and hydrogen bonding is also responsible for the structure and activities of biologically important proteins and enzymes. And you can see here helical structure happens because of intense hydrogen bonding between two such DNA strands that gives a twisted conformation, and one of the representative hydrogen bonding is shown here between guanine and cytosine. And when we talk about van der Waals, often students make mistake in writing the name, and one should remember van der Waals full name is Johannes Diederik D.I. So, this is the full name of van der Waals, that is called Johannes Diederik van der Waals, and when we write shortly we have to write only this one. That means we should remember small v and small d and capital W. So, this is how one should write, one should not forget about this one. Often I have seen students making mistake while writing his name. Okay. So, let us look into one more important compound of hydrogen, that is hydrogen peroxide. Industrial production of hydrogen peroxide involves the anthraquinone auto-oxidation process, where an anthraquinol dissolved in an organic solvent is oxidized using air to the corresponding anthraquinone, and hydrogen peroxide is formed. The hydrogen peroxide obtained is recovered by extracting the organic solution with water, and then the anthraquinone that is formed is then reduced back to the anthraquinol using hydrogen and a palladium catalyst. This process is repeated many times, giving a catalytic cycle. Let us look into it, how it is made. It is called auto reduction. So, this one on aerial oxidation forms anthraquinone, plus H2O2 is formed, and this one is in the organic phase. When it is treated with water, H2O2 comes into water, and that can be separated from organic layer. And again, to get back this one, this is anthraquinone, so to convert this anthraquinone back to anthraquinol, one should use hydrogen and a palladium catalyst as a reducing agent. Okay. So, you can get back and again pass hydrogen. So, this can be repeated several times to produce H2O2, and of course, laboratory method involves simple interaction of barium oxide, barium peroxide with sulfuric acid. So, this is laboratory method. So, in case of industrial method, anthraquinol is taken and it is treated with oxygen to undergo aerial oxidation to form anthraquinone, and H2O2 is formed. This H2O2 is extracted by treating this organic medium with aqueous, so that H2O2 moves to the aqueous layer and then it can be separated. And treating anthraquinone with hydrogen under catalytic condition using palladium catalyst, one can reduce this back to anthraquinol and repeat this cycle to get H2O2. And in laboratory method, one can simply treat barium oxide, barium peroxide with sulfuric acid to form H2O2, and BaSO4 is formed, it precipitates out, and this can be taken. When crystals of a compound, especially coordination compounds, are grown from a solvent, they may contain solvent of crystallization. If the solvent is water, that means if the crystallization is carried out in aqueous medium, the compound often get hydrated. The formula of the solvated compound shows the molar ratio in which the solvent of crystallization is present. For example, if you look into copper sulphate, often we come across the formula is written in this fashion, okay. Or it can also be pronounced as copper 2 sulphate pentahydrate, or one can also write so it represents the ratio is 1:5. Okay. And what are the importance of hydrogen in biology? Okay. Hydrogen is cycled by microbial organisms using metalloenzymes. For example, nitrogen fixing bacteria which yields hydrogen as a byproduct of ammonia formation. You can see those things here, various biological cycles in which hydrogen is formed as a byproduct is shown here. And some of the simple compounds of hydrogen are shown again here. The simplest ones are methane in case of group 14, and ammonia in case of group 15, and water in case of group 16, and also their respective shapes and also the geometries also you can see here. And let us look into the reactions of dihydrogen. And molecular hydrogen is activated by homolytic or heterolytic dissociation on a metal or a metal oxide surface, essentially by using D block metals. That means, if you want to do hydrogenation of unsaturated organic compounds, one can generate the active species from molecular hydrogen. For example, in case of homolytic dissociation, one can take on metal surface, what happens is hydrogen is split, homolytic dissociation happens, and it forms platinum hydride. That means both are H minus, they are formed by leaching out one electron from platinum, and it forms like this. And then in case of heterolytic dissociation, what happens, for example, if you take hydrogen over zinc oxide, here it shows heterolytic where H plus and H minus are simultaneously formed, and as expected H minus will be binding to O, and H plus will be binding to O, and H minus will be binding to zinc, and later this H plus or H minus can be transferred to the substrates in the process. We call it as hydrogenation reaction. Okay. And reaction of hydrogen with oxygen and halogens also involve often radical chain mechanism. Of course, when we talk about radical chain mechanism, we have to remember 3 steps: initiation of a radical chain reaction, and in here essentially what happens if H2 when it is treated with halide, it generates the 2 radicals I have shown there. 2 radicals are shown here, and these 2 radicals in presence of oxygen molecule form HOO dot, and then this HOO dot again reacts with this radical here to form 2 hydroxyl ions, and these hydroxyl anions in combination with H2 molecule gives H2 and H dot, and this H dot again participates, and this radical chain reaction continues. Okay. So, now let us have some questions. Classify the following compounds into ionic, covalent and metallic hydrates. We all know that alkali metals and alkaline earth metals form ionic hydrates because they are extremely high, extremely electropositive elements, whereas p block elements form covalent hydrates and transition metals form metallic hydrates. So, based on this information we can classify, for example, hydrogen sulfide, ammonia, PH3, aluminum hydride, all of them here up to here all covalent hydrates, and here they can be polar or non-polar covalent hydrates, whereas sodium hydride, calcium hydride, lithium hydride and beryllium hydride. Beryllium hydride has some covalent character, but nevertheless they are all ionic hydrates, and ReH9 2 minus is metallic hydride. In fact, this is one of the rare example of homoleptic transmetal halides. Here rhenium exists in +7 oxygen state and having 9 hydrogen atoms, and the geometry of this one is tri-capped trigonal prismatic geometry. So, now let us look into another question here. Classify the compounds such as PH3, cesium hydride and diborane and discuss their probable physical properties. For the molecular compounds, specify their sub-classification. So, that means whether they are electron deficient, electron precise or electron rich. By simply looking into the heteroatom that is present in the hydrates, we should be able to tell based on the knowledge we have about these hydrates. For example, phosphine, phosphorus is in trivalent state and phosphorus still has a pair of electrons intact. So, this is essentially a electron rich compound. So, it can act as it can act as a Lewis base. This is Lewis base, and cesium hydride, it is electron precise but ionic hydride. Okay, whereas B2H6 it is electron deficient, so it acts as a Lewis acid. Okay, so this is how we can classify by looking into the heteroatom and its electronic configuration. And let me summarize overall the chemistry of hydrogen I had discussed so far. Lightest element and the most abundant element in the universe. Okay, hydrogen is the lightest element and the most abundant element in the universe, and 3 isotopes are known for it, essentially having 1 proton, 1 neutron and 1 proton, 2 neutron, protium, deuterium and tritium. In the combined state, third most abundant on the earth's surface, essentially in the form of water or hydrated minerals. Industrial production involves water gas shift reaction from petrochemicals. The bulk of the production of H2 comes from petrochemicals, although we use electrolysis and other methods. And hydrogen bond dissociation is very high, it is about 435.88 kilojoules per mole, which is highest for a single bond between 2 atoms of any element for that matter. And atomic hydrogen torch generates a temperature of 4000 Kelvin used for welding in high melting metals. For 3 types of, we come across 3 types of hydrides when hydrogen interacts with any element in the periodic table. They are ionic hydrates, covalent hydrates and metallic hydrates, and all hydrates are good reducing agents and they are ideal source for cleaner energy in future. I wish I had time to discuss about the hydrogen fuel cell for renewable energy as an alternate source of energy. However, before I complete this course, I shall talk about hydrogen fuel cells at some point of time. With this, I conclude the chemistry of hydrogen. In my next lecture, I will be focusing on the chemistry of group 1 elements, that is the chemistry of alkali metals.